All right, so here we have my simulation for the evolution of a small parts sorter. So currently this is low generation. We have basically generation 1 done. We just have 120 individuals currently submitted for generation 1. And this is the best option that it came up with. You can see the Legos or the small parts are going to drop down here. It has a small pegboard that it goes through. Some ramps are just in random positions through this evolution. Then it goes through the detector here. I currently have a system where in case some pieces fall off the edge or whatever, they captured this yellow detector, that counts as penalties. We have some individual hyper parameters that we can set up with some different fitness weights to make sure that the system evolves in a way that we would like to, and see how our fitness parameters in our equation impact those. Then additionally, we have for the best run some individual data here so that we can assess what is happening, because we do turn the small parts off so that we can get a better speed of rendering behind the scenes. So we can see currently in this generation most of our pieces did end up in phase clump of 1, and we had a few that were in clumps of 2, but we can see our distribution here in time is pretty poor, that the majority of pieces are being separated by just a few milliseconds, and we obviously have set up our system where we want a singulation pattern, so we're looking to get a relative interval distribution somewhere between 200 to 500 is where our current equations are. So in this low resolution system here, we have majority of our pieces just coming off as quickly as possible. So as the system evolves better, we'll have some more of that. And then here we can see that we have some historical data of a different simulation from this run here. So we have 38 different generations. We can see that our average mean fitness population was increasing. We had our mean fitness of the top 20, which I find is important to look at, was also still increasing, and that our best individual fitness had peaked relatively early and was still kind of fluctuating in this range here, as what you'd expect for taking your best chromosome and then retesting it a few times. Then we can see that our fitness standard deviation was going down, and because this is a hyper-aware evolution system, because we didn't get a significant amount of improvements over a significant amount of time, our evolutionary mutation rate went from 5 all the way up to about going to 20 eventually. All right. We can look and see how the evolution was occurring over time. We can see why and how we had different failures. Currently, looks like we only had stuck piece failures. They peaked for a while, and then we're going down close to a value of 0, which is what we would hope to see. We can see our run completion deals to save time. We look at things like stagnation. If the pieces aren't moving that fast, they're stuck, we abort the runs early, and so we still have a large number of those. The number of completed runs that we have are increasing, but you see they're still pretty low relative comparative to everything else, because we are trying an infinite solution space right now. And then we have our individual best performances over time, and then we have different penalty scores of those individuals, looking at like different aspects of their functionality. All right, what else can we do here? Let's stop this. Let's go to the cartographer. We're going to put this into this window here. All right, and then this is where we look to see how evolution occurred over time based on principal component analyses, so that we can take all the different variables that we change in our different simulations and see how they affect. So right now we're looking at the timeline of each generation, and then right now we can look at like what the computer decided was principal component number 1, and then we can color this towards fitness. We can see that we have an increased amount of fitness based on the color here, and that we were increasing the value and narrowing in on some optimum range in whatever principal component analysis 1 axis was. So we could go to the analysis chart that I have to say, well, what is principal component analysis 1? We see it looks like that is dealing with the funnel positions of the bottom of the system here. So machine height, funnel position 6 and 7, which are the bottom, was strongly determined by this. And then we have anti-correlations of the vibrations here. So principal component 1 is not vibrations, but instead the physical shape of the system here. And it looks like principal component 2 is also dealing with the physical shape of the system as well. So we can look through this to our heart's content. We can also get a summary report to see what the biggest impacts were for each principal component that we have. And then we can go through and see our trend analyses for these. Looks like right now my computer is having a hard time rendering the graphing for all of this, but we can see that we have some trends increasing and decreasing over time. So principal component analysis 1, if it was going to show up consistently, would be increasing, so that we are varying these two variables, as well as principal component analysis 3. But when we look at the variables that were organized in principal component analysis 5 through 10, we could see these are pretty much flatlined. So we could use this analysis here to identify the principal component variables 5 through 10, whatever those are, and they probably are significant, are probably not necessarily related to our solution space, and we could reduce our solution space significantly based on this quick analysis, focusing on principal component 1, 2, and 3. All right, that is the evolutionary system that I have created from scratch.